the idea here is that we build a record, mine, generate, and validate framework. The basic idea here is that we would like to record low-level data with very low overhead. And then we would like to mine this data and translate it to high-level representation. And then we would like to use the model to generate test cases that will be validated on the real device. So the first step, we designed a solution which relies on get event utility, which is part of the Android operating system, which essentially allows you to collect low-level data that the users actually do with the application on the phone. So this is kind of data that you would be able to get, for example, by running on this application, right? This data looks like the following. So this is a typical look, and of course it's very hard to interpret what it means. But in fact, 6 lines on the top actually represent a single tap in a particular coordinate with a particular timestamp. So we can easily say that we tapped in that particular location on the screen. Of course, from this script, you don't know what exactly you did in the application, right? At this point, you know that you just tapped on that location, right? So you can collect a lot of data like that, and instrumentation overhead is going to be very low. In fact, you don't need to do anything with the application. Right? The reason you don't instrument the application, you just use low-level operating system utility to collect this load, right? However, the challenge here is that we cannot use this kind of data for anything, right? Because it's device specific, and we actually don't know what is going inside of our application. What ideally we would like to have, a high-level, GUI-level event sequence, right? So we would like to know which particular objects we interacted with. We would like to know type of action that we performed on that object. We would like to know where that object is located, in which window, in which activity, and of course we want to know the type of that object. So we would like to get from this information to some higher level information, okay? Some of you were at my talk on Monday, but some of you were not. So how do you think we can do this translation? Can we do this fully static? What do you think? Let's brainstorm for a second. That's a fairly interesting engineering problem, right? We can easily collect all these low-level blocks, but we would like to abstract them, right? Can we do this static? Can we do this translation fully static?
I think the operating system is doing this translation.
Operating system is doing this translation?
Android.
Okay, why do you think it's translating that?
Because I, as a programmer, I wouldn't have distinctive events. I wouldn't have an event on top says click and doesn't say press, release.
You're absolutely right. Operating system is handling those events, and operating system knows what that event does to the application, right? You're absolutely right. But if you're going to go with that kind of solution, it's first of all, it's not going to be. My question was, can you do it statically? Yes, you can do that, but it's not going to be a static-based solution, right? So in other words, you still need to be querying the operating system, right? So that would involve some sort of instrumentation at operating system level to get that information. Yes, you can do that, but ideally we would like to avoid it, because imagine telling users, we're going to instrument the operating system to collect the data, and we don't even want to instrument applications, right? So
only activating the value for
maybe, but in other words, what you're saying is a feasible solution, yes. Of course, it would have applicability limitations, but it is a feasible solution. But it would be a very technically challenging solution. You would need to basically hack into operating system, figure out where events are handled, and then basically say, okay, I get this event and I basically put it in the log. And I can do this translation by tapping into operating system, so I don't need to develop a translator for this task. Yes?
If I can modify the application, I can statically look to the code, look at the callbacks method, and then just point some point cut inside the code, and then collect all this information as a developer. I mean.
Absolutely, yes, you can do that. You can do that, and in fact, there are already solutions, existing solutions like that. They called in-field instrumentation, and basically you instrument the application and you run it in field, and then you get the crash and you get detailed information how you get to that crash, with all the stack trace, etc. But the problem is that we don't want to instrument our application. We don't want to instrument our application. So this is why we are relying on get event utility, which you will be able to use in the virtual machine as well to obtain these events, to interact with an app in an emulator and obtain those events. This utility does not require instrumenting the application. So as I said, this is what we get. This is your phone. This is your application in the phone that you're working with. You just run get event utility that is going to collect all these low-level logs. This is a solution that we prefer. This solution has very low, negligible overhead. As a user, you're not going to notice a difference. We're not going to instrument the application. We're not going to instrument the operating system. We'll just ask to run this utility and send this log back to the server. So the question, can we do this translation, in your opinion, static?
Well, what we can do in a static fashion is to aggregate those events. Like you said, the first 5 or 6 events are actually one tap event. Okay, we can recognize that.
Yes.
But any further abstraction, which button was affected or something like that, in a static way, I don't think so.
You're absolutely right. You're absolutely right. We cannot get that information. We actually have to execute the application in A. But what you just said is also important, because we need to get that log, and then we actually need to reverse engineer these actions from this log as well, right? Because we would like to be able to issue a command. If we want to rerun these things from this log, we would like to reverse engineer all these things that happened, and we need to fire them on the phone exactly in the same way, right? So this is the basic idea behind record and replay service, right? We're going to collect all these events, and we're going to replay all these actions, right? And that's exactly what we do here. So in order to get from these low-level UI events to these higher-level GUI-level event sequences, and by the way, these are type of tokens that we would like to set up on purpose, which essentially are tuples. We have GUI component that we know belongs to certain window, which appears within certain activity, and we know that in this particular case, this is the action that we performed on this GUI component, and this is the type of this GUI component. So these are examples of these tuples. This is the data that we would like to get from this low-level event trace, okay? Which is in this case is readable, and we can understand exactly what is happening here, right? We can say, yeah, we have main ID editor action cancel. We clicked on that widget which belongs in that window, which belongs in that activity. In this case, task list activity, right? How do we do that? We do it in 2 phases. In phase number 1, we have all these users who are using this application somewhere in the field. They're running get event utility to collect logs. After that, all these logs are sent back to the server. And on the server side, we actually have to cluster these event logs to be able to reverse engineer these commands so that we can actually do things on the phone. Like in this case, we know that we need to tap in this particular location. And this is why we have get event translator that essentially clusters this log into these commands that we can execute on the server. So in this case, this execution is done by relying on Android debugger bridge. This is, again, a system-level retailer that you can use to actually communicate to your application. So this is one of those foundational building blocks if you're going to be building areas in this tool, that you will know these kind of tools and commands very intimately, because these are tools which are your friends. right? They will allow you to communicate to application running on your device, application running on the emulator. So in this case, we are telling this device to tap in this particular location, okay? And then what we do, here again, this is done on the server. So here we can do anything that we want. We don't care about overhead, right? Here we are talking to the utility, which is an SDK utility called UI Automator, which I showed you in the last part. And UI Automator gives us UI hierarchy, or the snapshot of the application state. So basically, imagine that we have this information before and after executing that tab. Okay? What can we do with this information? We can do a lot, right? We can know exactly what happens with the application when we tap in that particular location, right? First of all, we know what is in that particular location, and we know what happens if we tap on that object in that particular location, okay? We have basically all the information about the objects, all the properties of the objects, and this is the essential idea behind this translation step. So we are getting these low-level events, we translate them into ADB commands, we run these ADB commands in step-by-step mode. And then at each step we obtain UI hierarchy of the application state. We're doing the differencing. And then we are inferring information that we need to obtain tokens at this level of abstraction, right? In this case, why is it good for us to have information at this level? What do you think we can accomplish with this information? Why is it important for us to get to this level?
So it's easy to replay.
Yes.
And to enter in the exact situation.
Yes. Yes.
The customer.
So in other words, if we have this button, and this is a big button, right? A concrete execution will tell us, I tapped in this location, right? Somewhere in the screen, right? But once I've abstracted it, I say, I have an area. I can click anywhere in this area, and I will generate exactly the same thing, right? Because it will result in sending that email, pressing that OK button and sending that email, right? What is it good for?
It's device content.
Exactly. So we are abstracting it from specific screen locations. Now, what we can do, we can record it on the tablet, and probably we need to rerun on the real phone. Of course, it's not as easy as it sounds, because we need to do a lot more work to be able to do that, because once we the alignment of the components is different, and it may, for example, not the whole object may show up on the screen, so we need to do a lot of reasoning, and we need to handle lots of special cases to be able to do that, but at least this will enable us to do that, right? What else do you think we can accomplish with this by abstracting these low-level blocks into high-level representation?
High-level logs are human readable to some
Yes,
extent.
yes.
So you can give that to some developer and say, check out what that guy did.
Yes, yes, we can do that, yes. But remember, we want to do better things with this. We want to learn. We would like to somehow utilize all this data that is wasted right now, right? And we're getting lots of these token sequences. We cannot learn from that low-level data. It's too concrete for us, right? Because basically, what's good it for if we're gonna say we have a million different instances of how I can click on that button, right? There is nothing else we can. This abstraction is absolutely necessary, right? Our goal is to learn natural usages of this application, right? So we want to know that we are most likely going to type our email before sending it, before trying to click send button, right? And we would like to reason at this level of abstraction. We don't want to reason at the level of tap and to tap on the keyboard to enter that symbol and do that 20,000 times before you click on the OK button. It's very unlikely that you will be able to learn any meaningful or useful transitions. Yes, you can try to build a model from that level, but it's going to generate so many false positives that it's not going to be useful in this particular context, right? So I'm just trying to connect a little bit two things here, right? On one hand, I'll get into that in a minute, how we use language models to do that. But also I'm trying to get to the point that we need to do a little bit more engineering to get to the point where we can actually meaningfully use language models in the context of this particular task, right? So in other words, you cannot just get the data, slap the model on top of it, and think it's going to work. In this case, it's not going to work. You have to extract the data before you can learn from it. And as I said, on one hand, we have the traces that we collect from real application usages. And on the other hand, we may not get data on all the transitions, obviously, right? We still would like to have more, a little bit more complete models, so we also analyze APK. In this case, we do static analysis to understand who components are, what kind of registered callbacks we have for those components, so that we can also add some of the missing transitions into the model, right? Which we may not necessarily observe at execution of runtime. And then the idea here is that we would like to build a model. And Fran did, again, amazing job presenting this topic yesterday. What I would like to highlight is how we cast this problem. Because here we're dealing with event sequences, okay? And what we would like to do, we would like this language model to generate usage scenario, right? We would like to generate sequences that would be useful for us in this particular testing context. So here, again, let me just quickly repeat. As you know, we have a corpus of these events, and the idea here is basically calculate maximum likelihood estimated parameters of this distribution that rely on language model or in-grid model. And essentially, we're trying to estimate how likely the events are to follow some other events. So in this particular case, let's say we have 4 grams. In this particular case, we are relying on this prefix to estimate probability of this event, right? And the way we're going to estimate probability of this event is by counting all 4 grams, which have this particular prefix, right? And we're going to count all exact 4 grams. So in this case, we're interested in probability that this event follows this particular sequence of events, right? So we're going to basically count all instances of that particular program over all 4 gram which has that prefix. And it's going to give us maximum likelihood frequency count for that particular event segment given the prefix. Of course, in reality, we have data sparsity issues, right? So yes, we're going to have 100 users, maybe thousands of users using this application, but still we're not going to get some transitions, and those transitions are possible transitions. So in this case, we are also applying 2 smoothing techniques. The one is known as a backoff model, and the intuition behind backoff model is that we can back off to models of low order. So for example, if we didn't observe that particular program in our corpus, we can back off to 3 gram model, okay? And then we can use this model to estimate this particular probability. And interpolation model, they use lower order models anyway. So this is the intuition that we need to understand. So having all this in mind, we essentially designed several different flavors of our testing engine. Essentially, we use both interpolation and backoff, but mostly important that our intuition was to design a sampling engine that would be able to sample from natural distributions as well as unnatural distributions, as well as combinations of those distributions for the sake of because we would like to be able to model natural usages of the application from data, right? And we call this up strategy or natural distribution. The idea here is we would like to sample most likely events given a prefix to events, right? So if you are typing a lot of text in this particular window, you're likely to send an email, right? Or you're likely to save it. These are very likely transitions, which ideally we would be able to generate with this up distribution, versus down distribution, these are less likely events that is going to happen given that prefix. So this is something that a monkey is likely to give you, right? Because monkey is likely to give you something, right? And of course, it would be nice to see what happens to probabilities in that case, in given context of that particular application. But this is what we're trying to do here. We're trying to surprise what may happen given that particular prefix. And this is a strange, that we call strange flavor. And the idea here is to generate some part of the scenario using natural distribution and once in a while inject events from their natural distribution. Okay? And we've actually evaluated different combinations of these flavors. So all these three flavors, we've used them with different smoothing techniques. So in this case, we have up interpolated, up back off, and the same thing with down interpolated, down back off, strange interpolated, and strange back off. I'm not going to show you all the results, but I'll show you some snapshot results in a second. But the idea here is once we have the language model that we built from this data, now we have a component that we call chimp. And the goal behind this component is to actually generate real commands from these task cases generated by the language models. So we have GUI sequence, which is our task case. And chimp essentially takes this particular GUI level sequence and translates it into the set of ATB commands that you saw in the previous example, right? So basically it takes this GUI sequence, which tells chimp, scroll on the list, click on this item, click OK button, and chimp says, okay, now let me think in Android language now, right? Or ATB language. So I'm going to tap here, I'm going to tap here, I'm going to long swipe here, I'm going to tap here, and generate the respective sequence of ATB commands for this GUI level sequence. This is a great opportunity, as we discussed, right? Because we can build device-specific translators here, right? We can plug in here different functions for Samsung, for a tablet, for different dimensions, for different modes, portrait, landscape, and we can do this translation. Essentially, we can plug in different modules for different versions of the phone on the phone. So here you already see that we can do record and multi-device and multi-platform replay just by relying on this solution. I'll show you example of the prototype that we have based on this idea. Now, chimp converts these commands and runs these commands on the real phone. And chimp works, as of today, in two modes. It works in serial mode and interactive mode. Serial mode means chimp says, give me 100 events, given this particular language model. Okay? And then what it does, it tries to execute all of them, one by one, of course. But at some point, we may get a situation where we will get some invalid events. And this is actually a fairly well-known problem with language models in testing context, because there are some couple of really good papers by Paulo and Ella from ICSI 2014 that there will be lots of infeasible sequences here, right? So in order to tackle this problem, we also designed an interactive mode where we sample events one by one and we check their feasibility before adding them to the test case. So the idea here is chimp gets event from the language model, given a particular flavor and smoothing technique. And then it tries to run that event on the phone. And if that event succeeds, we add this to the test case. If that event fails, we ask for another event. Okay? So this is the idea of interactive mode. And eventually, we get to the fully working test case, which can be replayed and reproduced on the phone. So as I said before, record, mine, generate, and validate framework was and still is a very substantial engineering exercise because we've been evolving and building on top of it for many other different tools, and I'll show you some of these tools today. Just to highlight a couple of things for the record phase, we are mostly relying on standard Android utilities like get event command to process the logs. But we also have for the mine phase, we, for example, build our own translator. We are relying on tools like, obviously, on all these compilation tools, bytecode analysis tools, as well as static analysis tools like SourceML, which I would highly recommend to any student who needs to do some sort of lightweight static analysis for Java or C++ applications. This is an absolutely fabulous, robust tool to use. Have you heard about SourceML before? I'm just curious. Can you raise your hand? Of course, good.
Yeah.
But also I can see some students, so do you like the tool?
I just heard about it.
Okay, just heard about it. Well, anyway, it's fairly robust. It's designed by and maintained by researchers from Kent State University. Actually, they've been building and maintaining this tool for, I don't know, more than 10 years by now. It's one of the most frequently used tools in our research community. Basically, whenever you need to extract facts from the application, that's one of the tools we're relying on. I believe it won most influential paper award at ICPC 2015. Yes. Also, here we obviously implemented a bunch of other tools. We are also relying on utilities like UI Automator, Hierarchy Viewer, as well as many other tools. So one particular story which I wanted to tell you about this paper, because I somehow wanted to echo really nice stories that Robert told us the other day about his experience on publishing and revising papers and then battling and sometimes or trying to win those uphill battles. This paper actually was one of those uphill battles. We originally submitted this paper to ICSI 2015, and it was pretty much badly rejected. It clearly was rejected by testing people, basically saying, fabulous idea, but you know, your code coverage is not amazing, and this and that. And this was very, very discouraging for my students, because we did spend a lot of time, tremendous amount of time building this, and we got fairly straightforward rejection. So my take on the advisor in that situation was, of course, there are some very good comments that we can address, and we can improve the paper. Of course, we can strengthen the evaluation. I'll show you the evaluation in a second. Obviously, you will see that this is less than ideal. But the point was, students spent a lot of time, and we had the paper rejected. What do we do? It's bad for my group's morale, right? We invested so much time. One solution that we actually decided on was to resubmit this paper to the second tier conference. We resubmitted it eventually to MSR. And the paper was accepted, and when the paper was presented at MSR, people loved it. So basically, Mario presented this paper at MSR. We got a lot of great feedback. People really liked it. Mario got unofficial invitations to apply for assistant professor positions at a couple of Canadian universities. So it went really, really well. And one interesting point here is, of course, the audience, who will be reviewing and deciding on your paper. And in many cases, we should do some meta-analysis at some point. It's very, very important, right? I don't want to delve too much into that, but this is one of those decisions I don't really regret, even though this work may not be as visible as if it were published at some other conference. But at some point, you need to make, as an advisor especially, you need to make these decisions. We've done a lot of really cool stuff on top of this, and I'll show you that in a second. So I sort of don't hesitate for a second that that was the right decision, that we published the paper at MSR and didn't wait for some other deadline. So how do we evaluate this, right? Because you can say, of course, you can compare this tool to other tools, and you can compute coverage, and you see how well it does compared to other tools, and then you're done, right? You just do whatever other papers did. Of course we can do that, that's not a problem. But this is not the point of this work. The point of this work is we're trying to solve something that no other paper tried to solve before. And what we're trying to solve, we're trying to use real data to generate test cases that represent natural usage scenarios of this application based on real data. No other approach is trying to do that, okay? Yes, of course we can compute coverage, but what we really need to evaluate in reality is how natural these generated test cases are, right? And actually one surprising observation is that in our reviews, none of the comments were with respect to that. Most of the comments were, your test coverage, your code coverage is not good enough. It's not good enough for those tools. So anyway, I'll show you both numbers. To do this evaluation, we recruited PhD students who used these applications. We gave them Galaxy tablets. So they basically used these applications for 15 minutes each. This was the data that we collected and translated from. And we compared Monkey Lab to systematic exploration. This is our implementation of DFS. And we also compared it to Android Monkey, which is the tool that we extensively discussed today. So this is just a snapshot of the results. You can go for more results in the paper, but what you can see here, you can see different code, in this case, statement coverage values for different language models, for different flavors of language models when it comes to code coverage. So here, this is a flavor which is based on interpolation on backup models. So these are all flavors for the serial mode, okay, across different applications. And these are the results for the language model which works in interactive mode with interpolation up strategy. So one obvious observation here is indeed interactive mode works much better than serial mode, right? Because you can generate more sequences with feasible events, and in this case, you obtain much higher coverages compared to serial mode. And in this case, you can also see that interpolation smoothing techniques works a bit better than that. This is actually statement coverage when we compare Monkey Lab to statement coverage obtained by other techniques, and this is statement coverage that we obtained from real usage data. So this is statement coverage from people running these applications. As you can see here, we're doing much better than systematic exploration and Monkey. However, we are missing quite a few of these transitions from the real data. And of course, keep in mind that this is a parameterized approach, right? So the statement coverage values here will depend on things like the size of the test case that we're generating, type of the flavor that we're using, etc., as well as obviously the amount of the data that we can supply to the model. Another interesting